Okay? And in that research, in the research that I did, I reached out to Hershey's and they said, hey, what they do is they make the proportion of dark chocolate 0.2, the proportion of crackle 0.25, the proportion of milk chocolate 0.3, and the proportion of Mr. Good bars to be 0.25. And I say 180 candy bars, but it turns out that I've already counted how many candy bars were in this bag. I just gotta do some real quick adding. And there was, in fact, 120 candy bars in this bag. So my sample size here is n equals 120. Everybody good? So, Hershey's made this claim. My question is, how many of each would you expect? We multiply 120 by each of the percentages, yeah? So what's can somebody help me out for the dark chocolate? What is 120 times 0.2? And I can do the crackle and the Mr. Good bars because that's a quarter. So 30. So I'm guessing the other one is 36, I would guess. Yeah. All right. So this is what we would expect to happen. Yeah? Now, how many of you guys think that the sample matched the claim? Do you think it was close? All right, so turns out I counted them. Gotta look at my cheat sheet. Everybody good? So, so as we can see, the sample doesn't quite match what we would expect to happen, right? So the question we have to decide is this difference significant? What are your thoughts? So it's weird, right? Because I look at this one, well, that one actually does match, right? What we would expect. This one doesn't match, but is that significant? I'm not thinking that's a significant deviation from what we expected to happen, right? But these two are starting to feel a little far away. Is everybody with me? So what we have to do is start to think through, like if I want to decide, is our sample far enough away from our population that I want to say that, hey, that original claim of these proportions in the beginning is wrong. And it's hard to do that because I can't just do z-test the whole time. Or if I did, I'd have to do a z-test for just this category, a z-test for just this category, a z-test for just this one, and a z-test for this one. That sounds super annoying because I don't want to do 4 z-tests. Is everybody cool? So this new test that we're going to learn, this chi-squared, is called a goodness of fit test. A chi-squared goodness of fit test is what we do when we have lots and lots of proportions. Okay? So here's the deal. What we're going to do is calculate what we call the contributions to chi-squared. So what we're going to do is we're going to take for each category here, the observed minus the expected, we square it, and divide by that expected count, okay? So for example, if I'm going to do that for this first, for the milk chocolates, I would do 29 minus 36 squared over 36. And I get 1.361. And what we're going to do is we're going to do this for each category, right? So then the next thing I'm going to do is 30 minus 24 squared over 24. And each of, and so that would be, I think it's 1.5, I think. That would be 36 over 24, yeah? And then 31 minus 30 squared over 31. I'm sorry, over 30. And then I think this last one should be like 0.03 maybe, 0.033. Okay. And each of these is what we call a contribution. And then the value for chi-squared is the summation. Remember that sigma means add, okay? And so chi-squared is going to equal 1.361 plus 1.5 plus 0.033 plus 0. So this chi-squared value looks to be everybody good? What did I miss?
1.361.
So it's 2.894?
Yeah.
Okay. So far, do we understand in terms of how chi-squared is calculated? We just say how, and when we think this through, each of these numbers is in a way, it represents how far from expected we would be, okay? Like, why is it that these two values, their contributions were much bigger than, say, the other two values? These two were the two larger values for chi-squared because those were the ones where my observed and my expected were so far apart. Is everybody good? All right. So the next thing we've got to decide is, so now this is kind of like saying, it's kind of like getting my z statistic, my z or my t value from my sample, right? It's a measurement of my sample. And we have to decide, is this a crazy measurement for chi-squared or not? Is everybody good? So as we think through that, right now, I would hope that if I say to you guys, is this an unusually high value for chi-squared? You would say, I don't know. Because you guys don't know how chi-squareds behave. And the answer to how chi-squareds behave is also really wacky, because one of the things we have to think through is not just the fact that we had like these numbers, but how many of these numbers did we have, right? Because like if I had chosen Skittles and we were looking at red, orange, yellow, green, and purple Skittles, I would have 5 of these numbers being added together instead of 4. You guys see what I'm saying there? Same with like if I had chose M&Ms, or if I would have picked anything else that was some other sort of mixed candy. Starburst, there would be 4. Is everybody good? We understand kind of the, all right. So, before we can move on with, is this chi-squared value kind of crazy? One of the things we'll want to do is say, well, what do the possible values of chi-squared look like? So chi-squared in and of itself has its own distribution. So I'm going to copy this because we're going to need it later. This formula for chi-squared is written on your formula sheet. So you wouldn't have to memorize it. You just need to be able to recognize that what you're doing is finding the contributions here for each category, yeah? Okay. Now, okay. So the first thing for chi-squared is chi-squared distributions are all skewed right. They are not normal, so we will not be having a normal condition. Okay, we're going to have a different condition. All right, and so, and chi-squared distributions also have a degrees of freedom. But our degrees of freedom are not the number of observations in our sample anymore. It's about how many numbers get added together. Okay, so for the test that we're currently doing, the chi-squared goodness of fit test, our degrees of freedom will be our number of categories minus 1. So in this case, my degrees of freedom is going to be 3, because we had 4 categories minus 1. Now, just like when we were doing z-tests and t-tests, you could find a p-value using that. If all you have is the test statistic, our test statistics so far have been z. We use normal CDF. They've been t. We use t-CDF, right? Our new test statistic is this value chi-squared. So I'm going to bring up my distributions menu and see. In fact, if we scroll down a little bit, if you need to, you have a chi-squared CDF. Does everybody see it? So I'm going to go down and choose that chi-squared CDF. Our value for, it's going to ask you for a lower and upper end degrees of freedom. So when I'm sketching this one, we said all chi-square values are skewed right. Our degrees of freedom is equal to 3. Our test statistic was 2.894. And so far, whenever we've shaded something for a test, we've shaded more extreme. The observed sample or more extreme. When we're dealing with more extreme for chi-square, more extreme is to the right always. So my lower, I'm going to put our value, which was 2.894. My upper, some really big numbers. My degrees of freedom, 3. Oop. Have an extra comma in there. We're finding a p-value of 0.408. So you guys, are our differences significant? Are you guys not getting 0.408? You got that? Okay. Are we good? Okay. You guys, so previously I said, are these differences from what we'd expect significant? What do you guys think? How likely could we have gotten that sample by chance alone? That sample or further away? It's a 40% likelihood this 0.408, this is my p-value. I would not call this significant. It's very reasonable that it could have happened by chance that we get that wacky of a sample. Are we good? So chi-squared measures what I would call the wackiness of how far from, it describes how far my sample is from what I would expect if the claim were true, okay? All right, so what we just ran was something called a chi-squared goodness of fit. You are always allowed to abbreviate goodness of fit as GOF. It's not a problem whatsoever. Okay. All right, so if I'm going to describe, so our null hypothesis, we could either do it in symbols or we can do it in words. So like, for instance, it might be that my null hypothesis is each of those proportions. If I were going to say that exact same thing in words, okay, it would be the distribution of candy types matches Hershey's claim. My alternative, it doesn't match. And as long as one of them, if you decide to go in words, as long as one of the hypotheses is written in context, that is sufficient for me. Now, in order, if I put my hypotheses in symbols, do all of these have to be incorrect for my null hypothesis to be wrong? So if you're going to do it in symbols, you might say P, I'm going to say, at least one, I'm going to say P sub I is incorrect. P sub I being the true proportion of candy of that type. How are we feeling? I got great news. For our conditions, only one of them has changed. Random, we're still going to look for is it given. Independent, we're still going to use our 10% condition. Okay? We do not have a normal condition because my sampling distribution in this case is the distribution of all the possible values for chi-squared I could have. And we just said chi-squared graphs are not normal. But in order for us to use one of these chi-squared distributions, we still need a large enough sample size that the predictable distribution would apply. Okay, so our rule for large sample size, this one's new, is that all your expected values or expected counts have to be greater than or equal to 5. Which, if you think through are each of these, assuming that my one bag of candy is a random sample, which is a large assumption, okay? But if we assume that all of these conditions will be mixed, our expected counts for what? The lowest expected count was 24. Everybody good? All right. So, we have to be able to calculate chi-squared. Our value for chi-squared was 2.894, right? And we found our p-value to be about 0.408. I want to show you guys real quick. This is just me copying from the previous page. I'm going to show you how we can put these into your calculator. Okay? Typically what we do is we put the observed into L1 and the expected into L2. So I'm going to go to Stat, hit Edit. It doesn't actually matter which one you put in where, but you need to know where you put them in. So what I like to do when I'm given the list is just kind of write it down so I make sure when I run the test, and I'll show you how in a second, okay? So 36, 24, 30, 30. All right, now, where have we found the shortcut to every test that we've run? We've hit Stat, we arrow over to Tests, and if you scroll down, you will see that option D says chi-squared GOF. Is everybody good? It says observed L1, it says expected L2. So let's say you put the expected in first, you have the ability to switch them here. So you just want to make sure you know where you put the observed list, where you put the expected list. It is not smart enough to know your degrees of freedom, so you got to tell it. You go down and hit calculate. And you'll see it gave us the chi-squared value. It gave us the p-value, and it actually gave me each of those contributions as well. Everybody good? So if I were to write a conclusion from here, I might say, since 0.408 is bigger than 0.05, we fail to reject our null hypothesis. We don't have enough evidence to conclude the proportion of each candy type is different. From Hershey's claim. New kind of test, but the reasoning is all the same. There is no chi-square confidence intervals because there's not one thing we're trying to estimate with a chi-square value. Because the whole purpose is we have many, many things that we're trying to make conclusions about. Everybody good? Let's go through another example real quick. So, as we read this, we have small, medium, large, and jumbo boxes of cereal. And we have claims for the proportions for each of these. Are you intending to call me right now? In the middle of a lesson? You are very important. Are you going to pick that thing up? I didn't. Okay, do you want money? Okay. Yep, bye. It's weird for Mrs. Wainscott to be calling me, right? Like, Mrs. Berlin, totally normal. Mrs. Wainscott, it's a little bit weird. Anyway. Are we good on our null hypothesis? And you guys, if this is my null, if I write my null in symbols like this, what should I put as my alternative? At least one of those categories, at least one of proportion from one of those categories, and that I is kind of like a general for all of them, is wrong or incorrect, where P sub I equals the true proportion of that size cereal sold. Can you guys keep a secret? We're getting an ice cream cake for Mrs. Bean for a meeting after school today. But Dr. Lee is going to be in that meeting, and she's gluten-free. So do you guys mind if I text Mrs. Wainscott and say, get one dilly bar? So that Dr. Lee can also have some ice cream. Do you guys, because I just thought of it and I'll forget it. You guys get what I'm saying, right? And yeah. We can all agree that Dr. Lee deserves ice cream that she can eat, right? Yeah. But you guys, only me and Mrs. Wainscott know about this, okay? So Dr. Lee doesn't even know, so we gotta be. Can you get like one dilly bar that is gluten-free for Jolie? Oh no, it's trying to do that in the context instead. Can you get at least one dilly bar since Jolie is gluten-free? Okay. Sorry guys, I appreciate your patience. What do you guys think I should do next? Before I do my conditions. We've always done something else after stating our hypotheses. We got to name our test, which is going to be a chi-squared goodness of fit test. I'm sorry? Yeah, absolutely say GOF. It is standard for standard across statistics. Nobody would have a problem with that. And if they do, they can come see me. You know what I'm saying? Okay, so random. Given SRS. Okay, large sample size, and again, I am comfortable with you say LSS, that's fine. But we haven't, what do we need to do next? We actually have to find those expected counts, right? So let's see, if I have 120 transactions, how many small would I expect? And what I like to do, typically, a good habit is you can write the expected counts as long as they're near their counterparts of the observed, and I put the expecteds in parentheses because that's my way, just a way of communicating that's not the actual value. Okay, are you guys with me? Okay, and then let's see, that would mean 15% is 18, and the jumbo is 18, and then 60% would be 6 times 12 is 72. But I could be wrong. You should probably double check my numbers. Ever good? Okay, and then I might say 12, 18, 72, and 12 are all greater than or equal to 10. And by 10, I mean 5. I'm still in proportions mode. And then independent, I think it's reasonable to say 120 is less than 10% of transactions at a grocery store. Serial transaction, whatever you want to call it. Okay. And then from there, I think the next thing we're going to need to do is stat, edit, put these in. And again, let's say you don't remember that you're supposed to put the observed in first. It's fine, but if you're someone who's going to make that mistake, what I like to do is I'll put, I put these in L1 and these in L2, so like I can see it. You guys see what I'm saying? So that when I go on to the next screen, I can see where I put each list, if that's something that you're prone to do, which it's a pretty easy mistake to do, right? Now, the other thing is your calculator will not let you put decimals in for your observed count. So like when you do any chi-square test, if you put, like, if like, it would cause a problem, it wouldn't cause a problem here because all my expected counts are whole numbers, but it's reasonable that your expected counts might not be a whole number, right? If I had 125 transactions here, none of these would be whole numbers. You guys see what I'm saying there? Okay, so if you get an error, the first thing I would look for is, when you run the test in your calculator, the first thing I would look for is that those counts don't match. Or that, like, if it says domain error, it knows that whatever your observed list is should be whole numbers. And it won't let you put in a decimal. Does that make sense? So now that they're in, we hit stat, we are over to our test. What's our degrees of freedom here? 3. So I can see my, so I've got chi-squared equals 9.51. I have a p-value of 0.023. My degrees of freedom is 3. And my contributions, so for small, my contribution is 1.33. For medium, my contribution is 2. For large, my contribution is 1.68. And then if you hit that arrow key for jumbo, my contribution is 4.5. In whatever order, like those are in the order I put them into those lists, yeah? I might say the proportions of box sizes sold, or the proportions of different size cereals. Has changed. The previous proportions are no longer correct.